ideas that will come up in this decadal that they're put in context from the point of view of the experiments that we have right now and that we hope we'll have by the time that those come along, right? And I think one of the important things that is new to us in this field is the idea of using multi-messenger probes for cosmology. On the page here, what you're seeing is an example of GW 170817, the one and only event for which we were able to detect both the gravitational waves and the electromagnetic counterpart, and use so that we could use it for cosmology in a way that is analogous to supernova, with using the distance information from gravitational waves and the redshift from the electromagnetic counterpart. Now, if you go to the next page, you'll see the size of the, let's say, actually, you see an introduction there to the dark energy survey. So this is my area of expertise is more on ground-based surveys, and in particular, I'm a member of DES, which is a survey that was that completed just recently. And the key thing that I wanted to point out here is that DES was pioneering one aspect here of dark energy research, which was, by design, it was made to combine multiple probes of dark energy. Probes that you could detect, obviously, from the ground, but multiple probes. This meant doing a program for supernova and a program for wide area observation of millions of galaxies in over 5,000 square degrees. And nobody thought that gravitational waves would be a probe at that time when we were planning the survey. But once it became clear that it could be, we decided to incorporate that too. So I think that going forward, what we are seeing already, for example, in the decadal and also in the snow mass process, when people of other communities are planning future experiments for dark energy, and other science as well, what we see is that the tendency of multiplexing, the number of probes, and also combining observational data from multiple experiments and facilities. And that will mean facilities from the ground and from in space as well. The idea being that one single probe cannot give the full answer. And you will see in the next page what I mean by that. On page 3, you have one cosmological parameter, the rate of expansion of the universe today, and examples of measurements. This plot is a couple of years old, but it gives a good example of measurements made with different observables. The red ones are the supernova, and black there is a Planck, so CMB-based results. And the big discrepancy that we often talk about in this field is that discrepancy between the results that you obtain from CMB and the results that you obtain basically with every other observable. Now, is this systematic uncertainty that is creeping in, or is this really new physics? And if it is new physics, what does this mean for the fundamental physics of dark energy? What does it mean? We don't know. And in order to figure out and disentangle this, we need precision measurements, and we need measurements that we can trust in terms of control of systematic uncertainties. And that will come from a combination of different probes. And I think that there is an opportunity for thinking about new experiments in space that cover part of the parameter space that we don't cover otherwise. So going to the next page, I show in one example of another part of the parameter space that has to do with clustering of galaxies. This is a result that came out from DES, showing that also here we see as well tension between the results that you see from DES, that's the blue contour, versus what you see, for example, from Planck, which is green. This tension is not as prominent as what you see from in the supernova and CMB results, but it's there as well. And that's another hint for the size of the challenge that we have. On the next page, what I want to show is, I don't want to paint a too grim picture, but I decided to just take this triangle plot with the several cosmological parameters, including the equation of state of dark energy, W, taking the current DES results, that's the blue contours, and adding on what we would gain if we were to add, say, 8 gravitational wave events like 2017 or 817. And you can see that there is some movement there in the parameter space, but this is not precision cosmology yet. You know, to really do a precision measurement, we will need really to make a leap in quantity and also in precision in order to make this. And that's where I believe we should be thinking outside of the box into new experiments and new ways of doing this. Of course, there is a room for improvement because here I'm talking about only 8 events, but again, it's a challenge, but it's a challenge that I think it's really exciting because it is probably the only way we are going to be able to get to the bottom of what dark energy is, I believe. So on the next page, I'm getting already close. We can skip this one. So this was just an example of GW17, weight 17 again. And the next 2 slides are our attempts to repeat what we did with GW17 weight 17 in the last observing run of LIGO. And as you can see, we were not able to make a detection. We were able to put constraints on the parameter space of mass, velocity, and opacity of the ejected material in the merger of the 2 neutron stars. But we were not really, didn't really make a spectacular discovery like 2017 or 817. So this is pointing to the fact that we probably are not going to be able to rely on making one-to-one, detections like that in order to accumulate enough events to make a precision measurement. And that's where in the next slide, what I'm showing is what we've been pursuing today is the combination of bright sirens, the ones that have counterparts, with dark sirens, the ones that don't. The idea is that you can use statistically a number of galaxies in the region of interest to make the constraints. This plot is from a recent paper that we published showing the red curve is the combination of all of the events we've had today. The gray, for comparison, is GW17 or 817 alone, the one bright siren that we have, and the other curves are dark sirens by themselves. So as you can see, if you use in a clever way the events that we have, we can make a measurement of H naught, and that's what you're seeing there. But in order to distinguish between these 2 purple vertical lines there, which is representing supernova and CMB results, we are far from that. We really need to make a leap forward, and that is a challenge that we should have to face. So finally, in the next slide, I present a cartoon description of one way to go about this. And this will be to really fully utilize the entire range of galaxies in the future cosmological surveys. I'm thinking when LSST is done, or DESI and other surveys that will cover large volumes of the sky. Here, literally, it's just a cartoon that I made by hand, but it illustrates the idea that on one hand, you would have many gravitational wave events from a next generation survey, and on the other hand, you would have a vast galaxy catalog. And you can transform distances in redshifts and do the cross correlation of these 2 maps. And with that, make a measurement of the cosmological parameters that is analogous and uses the same tools that we use today for BAO and large-scale structure measurements. And I think that this is one way to go forward to try to really get greater redshift range and greater numbers, statistics of events to try to get the results that we need. So I will stop here and perhaps take questions.
Thank you very much for this talk. I do have one question. So you're focusing on DES, which as you mentioned is just finished up, and possible links to the gravitational waves. So my main question would be, what do you see in the future as the potential space for for dark energy direct detection via quantum techniques? And if you haven't thought about that, would you be willing to, in the next few months, help to think about that in the context of a white paper?
Sure. So the way that is really not one area where I've been really focusing much lately, but I'm really excited about it because I think what we would like to do is to have a way to translate what we see with these surveys, which is basically rates of expansion, clustering properties, etc., translate those properties into what the models for dark energy and the observables that you would have for direct detection and a lab-based type of experiment are, so screening parameters and etc. And I think that if we don't have this handshake between these two sides, we are going to be in a scenario where the two communities will be speaking at each other, but not really working together. So this is one area where I'm pretty sure that other people possibly other panelists here have more expertise and will be able to say more about that. But this is where I would be interested in being able to translate, the results that we expect to get into equation of state parameters and clustering properties of galaxies and so on, so that we can work, with the data in both ways.
All right, fantastic. Are there other questions about that first talk? And if not, maybe, yeah, thank you. Thank you, and thank you all the speakers. And then maybe we can move on to the second talk that's going to touch on modified gravity, and that's Jeremy Saxteen. So go ahead, Jeremy.
Okay, thank you. So you can go ahead to the next slide if you like, or please do. So I'm going to talk about what could possibly be driving dark energy and why it's interesting to test dark energy in the solar system and why we think that this is an interesting thing to do. So to me as a theorist, dark energy is really the statement that there's some mysterious thing out there that's pushing the universe apart and making it accelerate. And so to try and understand what it is, I like to recall this quote from John Archibald Wheeler, who was one of the pioneers of general relativity. And he said that space-time tells matter how to move, and matter tells space-time how to curve. And when you think about it from this perspective, there are only really two possibilities for what dark energy could be. Either it's some type of new matter fluid, which has some sort of negative pressure and pushes the universe apart, or there is some long-distance modification of gravity that emerges on very large scales. Maybe gravity gets weaker, maybe it does something funny, and this thing causes the acceleration of the universe. And today I'm going to talk about the second possibility, partly because it's kind of emerged as the leading paradigm amongst theorists, and partly because this is what allows us to test this thing in space, because it predicts new modifications of general relativity. So next slide, please. So I'm not going to talk about a specific theory in general, but what I am going to say is that if you really do think that dark energy is due to a modification of gravity or even any sort of new physics, then very generically, whatever theory you're interested in, whatever formalism you're using, this new energy scale emerges that I've called lambda. So people will refer to this as the dark energy scale, and it's a scale of order MeV, and it's connected to the energy density of dark energy in the universe today. And this scale is very important because it's the scale on which we expect new physics to emerge. And in particular, if we think that dark energy is some sort of modification of gravity, then at energies around this scale, we expect new fifth forces between matter to appear, and screening. So screening is a way of hiding these fifth forces within the solar system, and also violations of the equivalence principle, which underpin general relativity. So the reason that people who are interested in dark energy are interested in testing it in the solar system is that at this scale, we expect new fifth forces. And by looking for these fifth forces, especially screened fifth forces and equivalence principle violations, by trying to make a direct detection of them, we provide direct evidence of that dark energy is some sort of modification of gravity. So next slide, please. So I've mentioned screening mechanisms, and for the purposes of this talk, I'm going to split them into two broad categories. So I'm going to split them along lines of whether they're best tested using laboratory tests or whether they give long-range forces. So the first category is what I call thin shell screening. So for those of you who've heard of these before, these are things like Chameleon screening and symmetron screening. And these are really parameterized by very strong couplings to matter, in some cases much stronger than gravity. But due to the way the screening operates, they operate on very, very short ranges. And this means they're best probed using laboratory techniques, things like atom interferometry. So I'm going to defer to Claire's talk for a discussion of these forces. In this talk, I'm going to focus on the second class, which are called Vainshtein screen theories. And for those of you who've heard of these before, you may have heard of theories like Galileon theories or camouflage theories. And these theories are really characterized by gravitational strength couplings or even weaker, and they tend to operate on very large ranges. So on the next slide, which you can go to, please, I'm going to give you a toy model of how Vainshtein screening works. So Vainshtein screening works as follows. So what I've got plotted here is the sun, clearly, and the strength of the fifth force in Vainshtein screen theories depends on how close to the sun you are. So in these theories, this new scale emerges, which is called the Vainshtein radius, and I plotted it here. If you're outside the Vainshtein radius, then everything looks like an enhancement of gravity, and you just have some coupling constant alpha times the Newtonian force. But if you're less than the Vainshtein radius, if you're within it, there's a suppression factor by R divided by RV to some power n. So this is how Vainshtein screening works. You have this suppression at small scales. And if you just take the sun and plug in typical parameters for a dark energy theory, you find that the Vainshtein radius is of order 100 parsecs. So clearly, if this thing is dark energy, the solar system is deep within the screened regime. And in this case, the acceleration compared to the Newtonian acceleration is of order 10 to the minus 12. So this is a tiny number. So far, theorists have really been restricted to trying to come up with very clever ways of looking for tiny 10 to the minus 12 deviations around the Newtonian force. And for this reason, the constraints are currently not overly strong. I won't use the word weak, but they're not where we would like them to be, because you're looking for very small effects on a dominant force. And that's because of the lack of dedicated experiments. So if you just go to the next slide quickly, we should just change some of the arrows around. So in particular, we're looking for, actually maybe one more, yeah. So the two numbers we're interested in, oh, sorry, go back to one. So the two numbers that we're really interested in going after for these theories are the strength of the coupling to matter, which I call alpha here, and this value n. So each value of n will give you a different theory of gravity that could be dark energy. So now if you go to the next slide. One thing I wanted to talk about a bit was the PPN mechanism and its limitations for testing dark energy theories, and why direct detection experiments which are dedicated to these theories could really yield vast improvements. So what PPN really does is it's a parameterized framework for testing gravity in the solar system. But what it really does is it parameterizes the space-time curvature due to the sun. So it only accounts for one body effect. It assumes all the planets and everything else are test bodies. And this means that by definition, it doesn't include weak equivalence principle violations. And it also makes some very serious assumptions. It makes some assumptions that there are no new energy scales in your theory and no new mass scales in your theory. And in particular, this means it doesn't apply to dark energy theories, because dark energy theories does have this new scale in it. It has the dark energy scale. And for a lot of theories, it has extra masses that have ordered the Hubble scale. So again, dark energy theories don't really fall into the PPN framework. So if you go to the next slide. So for that reason, the best tests on some of these Vainshtein screen theories actually don't come from PPN. They come from thinking of very extreme ways of testing these theories. So right now, the best way of testing Galilean theories is by looking for effects of strong equivalence principle violations. And the way that theorists have come up with doing this is because black holes have a no-hair theorem, they don't feel the Galilean fifth forces. If you have a galaxy falling towards a larger galaxy in a cluster or moving in the cosmological background, the black hole tends to lag behind the galaxy and you end up with an offset. And so by looking for this offset in data, you can constrain the Galilean coupling a little bit. And so the most recent bounds, which came out very recently, are this blue region here in the right panel that I'm showing you. So on large enough scales, you can constrain it to be of order 1 or less. So if you go to my final slide, please. This is why a mission like Goddess would be really useful for testing things like dark energy directly in the solar system. So first of all, because it's designed to cancel the effects of Newtonian gravity, you're no longer in this situation where you're looking for a small 10 to the minus 12 effect on a very large signal. This 10 to the minus 12 effect is the signal. It's also not tied to PPN, it would be dedicated, which means you could try and test these dark energy theories without having to try and force them to fit into a framework into which they fundamentally don't belong. And in particular, because they're going to be very sensitive and very precise, you can look for very weakly coupled Galilean theories and try and go after this region I've indicated with a cyan arrow here, which can't be tested with these black hole offsets. So that's all of my talk. If you go to the last slide, I'm just thanking you, and I'll happily take any questions.
Jeremy, I had a quick question. If you go back one slide. Thanks. Yeah. So what is the main thing stopping the black hole work from going lower on that plot? Like, could it just more galaxies or?
Well, so actually, this actually includes quite a lot of galaxies now. So there are a few things. One, of course, there are always systematics when you're doing galaxy surveys, which you need to account for. You have to decide whether your signal really is an offset black hole or not, because you're not measuring the black hole directly. You're looking for differences between centroids. And then finally, if you go to very small scales, nonlinear cosmological effects become important. And this test actually relies on a key property of Galileons, which is the ability to add linear solutions due to the Galilean symmetry. So at some point you lose that ability.
Okay, that makes sense. So there is kind of a hard cutoff there, and we won't be able to go past that.
Yeah, I think at some point there will be a bit of a fundamental cutoff. I did discuss this with the author of this work, and I think you could make some plausibility arguments for going to smaller scales. But at some point, you really do need the linear field to be added, and at some point, the field is just not linear anymore.
Thanks.
Thank you, Jeremy. That's great, and I'm excited about your talk, moving us a little bit into how we can use direct detection to measure some of these theories, and I hope that we can count on you to be part of a white paper or multiple white papers going forward. Are there other questions for Jeremy? And if not, maybe we can move on to the third talk by Claire. All right. If not, let's move on to the talk by Claire. Thanks, Jeremy.
So hi, thanks for that. Can you hear me okay? Yeah, great. So yeah, this talk is going to build very much on what Jeremy has just been introducing. So if you could already go to the next slide. So Jeremy introduced these two concepts of screening. One where the Vainshtein screening that he talked about, where the amount of screening you get depends on your distance away from the source. So as Jeremy said, if you're inside the Vainshtein radius, then the phase force that you feel is suppressed. And what I'm largely going to talk about here is the second or the other type of screening mechanism, whereby your distance dependence stays sort of similar to that we're used to with gravity. You get a 1/r² fall off with distance for the force. But what we're doing here is changing the way in which matter sources that fifth force. Sources our scalar field, which is transmitting the fifth force. And I think probably at this point, in light of the plenary discussion, it's worthwhile saying that what we're looking for here really is fundamental physics, because we're looking not necessarily to understand exactly how the expansion of the universe is accelerating. We're saying, okay, I have a theory for why that accelerated expansion is happening, and that theory has these other consequences as well, and those other consequences are things that we can go and look for with dedicated experiments, dedicated missions, that will allow us to test whether our fundamental theories are correct. So the type of theory, fifth force screening that we're talking about here are ones whereby if you've got really tiny objects, then the extra fifth force that's coming from your dark energy theory is sourced by the whole object. So that's the small blue blob on the right-hand side of the slide is a small object, and the fifth force is sourced by the whole mass. But if we kept adding mass to that object and made it larger and larger, we get a picture that's much more like the sketch or the cartoon on the left-hand side, whereby you start to develop a central region of that object, which is in a different regime of behavior of the theory, and you're not sourcing the fifth force in that region. It's only a shell of matter, and potentially a very thin shell of matter near the surface, which can talk to your fifth force. So now if you could go on one slide for me. Sorry, could you change the slide for me, please? So that leads us to these violations of the equivalence principle, and leads us back to a very old idea for testing our fundamentals, fundamental physical principles, which is the question of whether large objects and small objects fall at the same rate. Now, we know that under gravity, they do. Gravity doesn't care about the size of the object. But in the presence of these new dark energy forces with these thin shell type effects, what you find is that if you have a small object, then gravity is pulling on the whole mass of the object, and the fifth force is pulling on the whole mass of the object, and that's pulling it down. Whereas if you had a larger object, gravity is pulling on the whole mass, but the fifth force is only pulling on a tiny fraction of the mass near the surface. And that means the smaller object feels much more force than the larger one, and so falls faster. Now, this is an idea that we have been trying to test for a long time. We've got very good tests of the equivalence principle all the way back to Galileo. So why is this something that we can talk about in the context of dark energy? And really the point here is that maybe we haven't looked at testing the equivalence principle either precisely enough or with small enough objects so far. So if you could go on one more slide for me, please. Now I'm going to go on to talk about doing these kinds of tests with laboratory experiments, but I think it's important to mention first that that's not necessary. You can do this with astrophysical observations if you want to. You can ask the question, for example, does gas, which is made of sort of very small dust particles, does the gas in a galaxy fall in a gravitational potential at the same rate that the stars fall? The stars are much larger and much denser objects than the gas molecules. And this is a test that's been proposed and that people have now carried out with recent galaxy surveys, and are getting very nice constraints on these models from doing this kind of observation. But as always, when you're trying to test fundamental physics with astronomy, you run into systematic problems that are quite challenging. For example, if you're looking for an offset on the sky between the gas in your galaxy and the stars, or and you're looking for quite extreme offsets, how do you know that the gas and the stars are actually associated with the same galaxy and there's not just a coincidence along the line of sight there? So this really motivates doing these kinds of tests in the laboratory, where we have much better control of the systematics, and we can really be sure what it is that we're trying to test. So if you could go on another slide for me, please. Yeah. So what is plotted here is for one example theory for a particular Chameleon model, which has two parameters: the strength of the coupling to matter on the horizontal axis and the strength of the self-interaction of the field on the vertical axis. And you can see the dark energy scale that Jeremy was indicating coming in there as the normalization on the vertical axis. That over a huge part of that parameter space, we can start to think about testing these forces with sufficiently small objects, because atoms, it turns out, in a laboratory vacuum are sufficiently small that they feel the fifth force. The whole mass feels the fifth force. There's no thin shell screening effects. The other advantage of doing things in the lab is that actually The walls of the lab act as another thin shell for your object, for your fifth force, sorry. And so they, as far as the new physics is concerned, they screen the interior of your vacuum chamber from the exterior. Now, for a laboratory experiment, that's an advantage. That gives you quite a clean environment where you have a very tight control of your signal. It's worth mentioning, though, that it can also be a disadvantage. So we've been talking about equivalence principle violations, and the microscope mission has obviously very recently been looking for those. But it's not sensitive to this kind of dark energy new physics, precisely because the whole construction of the satellite around the test masses screens any new physics effect from their sensors, from their detector. Okay, if you could go on another slide, please. So this is just to give you a very brief flavor of the kinds of experiments that have been done in the last. There's really been an explosion of these kinds of searches in the last roughly a decade, maybe 5 to 10 years. So there have been tests with using atoms as a probe mass, so atom interferometry. That's the experiment sketched in the top left. People using ultra-cold neutrons, bouncing them across a mirror, and using that to very precisely measure the forces experienced by the slowly moving neutrons. That's this cartoon sketch on the top right. And people optically levitating microspheres, so very, very tiny nano and microscale objects near a macroscopic source. And again, looking for the fifth forces, any additional forces on these tiny objects that we haven't yet seen on larger objects to date. And these are just a couple of examples. There are others. People have done neutron interferometry. If anybody is interested in seeing the whole scope, there's a review that Jeremy and I wrote a few years ago, which I've referenced at the bottom of the slide here. If you could go on one more slide for me. Their equivalence principle tests are not the only way of testing these theories. So I just wanted to mention, just to really have given you the full scope of what people are doing, because of the way that this screening mechanism works and the way in which the shells of matter at the surface of sources are very important. You actually find that if you can probe forces on very short ranges, you can see the effects of the dark energy force for a different reason, basically because things are changing very rapidly close to the surface of the field. And so a different set of tests are very good at looking for that kind of physics, in particular, the type of experiment that you would normally use to look for Casimir forces, so forces at extremely short distances. That's the right-hand picture, and also a newer version of that experiment in the bottom left. And of course, the Eort-Wash experiment, which has done so much good work in terms of looking for modifications of gravity. That's the top left picture, which also puts bounds on our theories of dark energy and the additional forces. If I could go on to the next slide, please. So then just to bring my talk together to show you the power of these types of measurement. Again, these are two examples of Chameleon models and their parameter spaces where the bounds of the types of experiments that I've been telling you about are plotted. And really, as I was saying, if you were to go back 10 years, the parameter space of these models would have been much, much more open, and you would have had a lot of freedom. And by thinking carefully about the phenomenology of the theory, how it behaves, and really identifying the best probes to look for the specific signatures, we've really been able to make a huge amount of progress in terms of understanding and constraining these models to the point where we're very close to being able to say that some of these theories are ruled out experimentally. I think that's it. Maybe if you could just go on to my last slide, I think I have a summary. So I'll leave it there, and if anyone has any questions, I'm happy to answer.
Okay, that's it, Claire?
Yeah.
Okay. Thank you very much. I really enjoyed that talk. Can we go back to the previous slide, slide 8? So one of my questions, I really like slides like these that show a parameter space and what we can understand from various methods. And so I'm wondering, you said things have changed a lot in the last 10 years. And if we look ahead, there's of course a lot of experiments in space and on the ground in the coming 10 years. And a space mission we start planning now probably has a timeline 10 years or more. Do you think that there will be an interesting discovery space for a possible space mission 10 years from now? Or do you think things will be shrunk by existing or planned astrophysics missions and other ground-based experiments?
No, that's a great question. I think if you're careful about what you choose to go after. So I've obviously presented this story to you as a success story of laboratory tests, but I've focused on one class of models, and you can only really these kinds of plots that Jeremy and I have put together, bringing together astrophysics and the lab-based tests. Sort of, you can only really do on a model by model basis. It's quite hard because these series are nonlinear. It's quite hard to do in a model independent way. And so it turns out that these particular classes of models that I've been talking about are particularly susceptible to laboratory-based tests. But there's a whole nother class of theories that you're never going to be able to probe, as far as I can tell, with lab-based tests. It's not, for these theories, it was a question of convincing experimentalists that these were interesting enough theories to spend their time on. Whereas for the types of theories that Jeremy was talking about, the signals that you would be looking for in a terrestrial experiment are just so small that they're beyond, the realm of what is possible in any sort of reasonably short timescale. So I think it does require talking to the community and checking and picking a sort of class of models as a target that are difficult to get in any other way. But then I think there's a real excitement about doing a space-based mission because you can't get at that physics in any other way.
Fantastic, thanks. Are there other questions for Claire?
Maybe just a quick follow-up question. So just basically exactly along the same line. When you said there are some theories that you can't test in the lab, and you said that I spoke about them, did you mean specifically the Vainshtein screen theories?
Yeah, that is what I had in mind. I guess impossible is maybe too strong, but I just think that the variations are so small on lab-based scales that it seems to me practically impossible to do.
I agree with the impossibility for Galileons. My question was going to be about the symmetrons. I know the symmetron.
Okay.
Changing the math.
So symmetrons, I think there are prospects for doing better still in the lab for symmetrons, thinking more specifically about their dynamics. But I'd probably not to the same extent of ruling out almost all of the parameter space in the way that we've done for Chameleon.
Yeah, so at least when I looked at symmetrons in PPN tests, it turns out the kind of symmetrons that were constrained were very different from the lab ones. So I was also wondering, is there a range of symmetron theories that could be tested in space that would just never be accessible on Earth?
So you're pushing me right up to getting me to talk about what I'm currently working on, but I have some ideas for this. I think that is something where there's going to be more to say, and I kind of don't. This is work in progress that I maybe don't want to talk about here because I'm not sure about the answers yet. But I think there is more to say both in the lab and in the solar system probably.
Okay, thanks, Claire.
I do have a question about symmetron model. So is symmetron less interesting than Chameleon, or I don't know, because I don't see much effort on symmetron sort of screening or symmetron constraint.
Right. No, thanks. So I haven't talked about the symmetron here because I was asked to give a short talk, and so I focused on one thing. Personally, I think arguably symmetrons are more interesting than chameleons. Certainly from you're coming at this from a particle physics point of view, it's a much easier to motivate potential than the kind of inverse power law that I'm showing you here. So partly we talk about chameleons more for historical reasons, that they were a theory that had been around longer and were better known at the time we started doing this work with the lab tests. So it made sense in terms of presenting the work to people to talk about chameleon models rather than symmetron ones. The same experiments do put constraints on symmetron models. They're not quite as powerful, and as I've kind of hinted at, this is something that I'm thinking about at the moment, kind of what you could do to do better for symmetron models.
Thanks.
All right, if there are no other questions for Claire, maybe we can go on to our final talk by Sheng Wei on the goddess mission concept. And then if people are around, able to stick around, I think there might be some good discussion or overall questions and planning after that. I'll try not to keep you too long because I know we're already over. So go ahead, Sheng Wei, when we get the slides up. Thanks.
Sure. Okay, so in the following 5-10 minutes, I'm going to present a mission concept that can really do measurement in space, hopefully. Next slide, please. So, well, you know all about this, that the dark energy is more than 50% of the universe, and the spread said that observation is one thing, and it's just really observe. And what we propose to do is, as other experiments, that we're going to do direct detection of dark energy. That is, we start from the equation of motion of dark energy models, and then we predict forces, and then we design experiment to measure the force directly. This way, we can really distinguish between different dark energy models. So I think that's a really powerful complementary approach to observation efforts. Next slide, please. So, well, you know all about this. There are screening effects on dark energy, and we have these screening mechanisms because we don't see dark energy right now in the solar system. So there are two categories, thin-sheet model and, well, non-thin-sheet models. And with thin-sheet models, atoms are good test particles for these kind of models, and laboratory efforts are making great progress. For the Vainshtein or Galileon kind of models, it's hard to do laboratory tests because atoms are as good as classical particles that, well, it's not better, so to say. So the bottom line is that experimentally, dark energy detection is hard because the force is weak. And theoretically, I don't think there's one dark energy theory that is consistent with all observations right now. But, well, even though there's no theory that works, more experimental constraints on different theories, different aspects can still point to new directions of what the ultimate theory might look like. Next slide, please. So as Jeremy pointed out, that the dark energy force is like 10 to minus 10 or 10 to minus 12 smaller than gravity. So to do direct detection, we need a very sensitive sensor. On the other hand, that means we have 10 to 10 larger signal as a background. That's just due to gravity. The problem now is that with gravity, we only know the gravitational constant to 10 to minus 4. So it looks like a mission impossible. So in our proposal, we proposed to use atom difframeters as sensitive sensors because atom difframeters are supposedly stable, and we can use these kind of sensors for long time averaging, and that can reach the sensitivity we need. And then we will design an experiment so that it's less sensitive or insensitive to gravitational field, so that whatever we measure is a direct indication of dark energy instead of having to correct for the gravitational force. Next slide, please. So atom difframetry, I think most of us are at least heard of it. So basically, when atoms are cold enough, like below 1 microkelvin, they go from classical particle to wavelets, quantum wavelets. With quantum wavelets, they can be split and recombined to interfere. So the scale factor for the acceleration and measured phase is really just fundamental constants. So because of that, there are some unique features of atom difframeters. First, we use atoms as free-falling atoms as inertial reference. That means whatever we measure is really measuring reference to a perfect inertial reference instead of having to correct for other things. Another thing is that the scaling factors are just fundamental constants. So in principle, the atom difframeters are stable and accurate for a long time. The last part is that atom difframeter works because of quantum mechanics works. So any test with atom difframeter is really quantum effect. So imagine that it's a comparison with quantum difframeter, atom difframeter with classical sensors. If there's anything different, then it may be due to quantum effect. And it's more interesting that the dark energy is sort of a cosmological scale, and we use quantum mechanics to test that. That may be something interesting by itself. Next slide, please. So we have this mission concept. It comes out of this NIAC study. So basically, we propose to have a constellation of 4 spacecraft orbiting in the solar system. So on each spacecraft, there will be atom difframeters as inertial reference. And then between spacecraft, we have laser ranging difframeter to measure the absolute distance, velocity, and acceleration between spacecraft. With this information, we can get a force gradient tensor, and then we can get the trace of the tensor. So we know that the gravity satisfies this 1/r, this inverse square law property. So the trace of gravity field is the trace of gravity gradient is 0, while the trace of other dark energy model is not 0. So with this, we can suppress the gravity effect sort of to the first order. And then, yeah, so this is a test of dark energy directly without worrying about gravity field. Next slide, please. So, so this is sort of put numbers to this goddess mission concept. So we use a cubic Galilean model as an example. So what we are thinking of is that we have a constellation of 4 spacecraft orbiting around the sun at a quarter AU, and with a spacecraft separation of like 80 million meters. And in principle, we'll get the gradient sensitivity like 10 to minus 22nd per second squared every 30 seconds. And the cubic Galilean model predicts that the dark energy field due to the sun would be like 8 times 10 to minus 24 per second squared at this distance. So that means if this mission flies, within 2 hours, we'll get signal to noise of 1 of this cubic Galilean signal. Next slide, please. So this is a tentative science traceability matrix. You can see from the left to right that we have science goals, and to the end, we have some mission parameters. So we can discuss this in more detail later, but just to show that we have some design, some thinking, and then we're looking to refine this kind of science traceability matrix. Next slide, please. So in addition to measuring the cubic Galilean field, Goddess can also measure other things. For example, Goddess use cold atoms as a sensor. That means probably it's also sensitive to initial models, but we haven't looked into that. Another thing is that Goddess, if you look closer, you can see that Goddess is actually 4 Lisa constellations or pointing in different directions. So Goddess for sure is sensitive to gravitational waves, and maybe this vector measurement will provide something useful or interesting. And Goddess looks similar to some of this dark matter detection scheme. So it's possible that Goddess can also measure dark matter. Since Goddess measures the gravity gradient tensor, so it can be used to measure a lot of controversial stuff like primordial black holes or planet 9 or tests of PPN. So a lot of things can be done with Goddess. So it depends on what's the primary science goals and what are the secondary objectives. Next slide, please. So yeah, this is the NIAC study team actually helped put this concept together. Yeah, so with that, thank you. And any questions?
Thanks, Shengwei. I guess I'll ask a question, then open it up. So my question is, what do you see as the hardest technical part of the mission, Goddess?
Well, so in principle, Goddess uses a lot of existing technologies, like laser ranging interferometer that's been demonstrated on GRACE follow-on, and atom interferometers are being developed in Europe and on the International Space Station. But the technologies need to be improved for this kind of missions. Like, for example, atom interferometers need to have more atoms, much longer interrogation times. That's only available in microgravity environment. So maybe there'll be some intermediate steps like tech demo missions for some of the technology demonstration.
Okay, great. Thanks, Shengwei. Are there other questions for Shengwei? If not, I think, Chris, you might have had a more general question or questions.
Yeah, so I guess I had some general questions for all of the panel, especially, I mean, yeah, so I guess trying to think about next steps for this, because there is this whole Decadal Survey process that's going to be happening, and thinking about the best way of putting all of these things together. I think the talks were pretty different. And so 2 questions, maybe we'll start with one, which is, what do you all think is kind of the best next step, both theoretically and experimentally, for putting all of these different things together and coming up with a cohesive plan that both includes the cosmology community and everyone else?
Anyone want to jump in? Any of the panelists want to jump in? I'm not hearing
I
anything.
don't know. I guess I would say
Go ahead.
it looks like you've got a pretty good starting point from the panel you've got right here, and maybe just build out from there as you need more expertise. I can't. Yeah, I'm not sure I have any other thoughts beyond sort of start trying and bring in more people as you need them.
All right.
So,
Well, go ahead, Chris. No, I didn't.
sorry. Maybe like a more pointed question would be like, okay, so there's a couple different things we can think about. You know, one on the theory side is what are the interesting theories that we should be thinking about, like specific theories. Another thing could be like, what are the parameterizations that we should be thinking about that actually encompass those and maybe go further than those specific theories. Then how do we combine this with the galaxy tests, these lab tests, and Earth-based lab tests, and the cosmological tests? Yeah, I think those are like the main things, and I wasn't sure if people had thoughts on any of these, or whether these would be good ways to demarcate like white papers. Yeah.
I'm especially interested in that last part of your question, Chris. If people have thoughts on whether we need more than one white paper or a single white paper, or where those lines would be. And so I'm not trying to present that as an original idea. I'm echoing Chris's question.
I mean, okay, I can jump in again if nobody else has an answer. I think my feeling is it might be better to although I would definitely be interested in what Jeremy is thinking as well. It would be better to think. I mean, there are a couple about the experimental methodologies you want to work with, or that it's possible to work with, and then we can see from there if there are interesting regions of parameter space to go after for those theories, and then what the best case is. And if there's more than one experimental methodology, I could definitely see that being more than one white paper. I wouldn't personally necessarily split things up by theory, because I think that probably ends up being a bit too bitty, and then each one becomes a bit too niche. But that's just my take.
Yeah, I mean, I agree with not splitting things up by theory. I guess we discussed this a little bit the other day, but one thing I suggested to Chris was just along the lines of parameterizations is that rather than going for, say, some parameterized framework like PPN, is just to assume a general force law with different couplings and different powers of n, and that would map onto a lot of the theories which are more difficult to test in the lab. So things like camouflage theory and Galilean theories. And something I suggested to Jeff Jewell, I think at the last workshop we had on this, was the potential of constraining the graviton mass using Goddess as well, because now that you've got the numerical tools to go ahead and simulate these fields, I think it'd be interesting to see what range of graviton masses you could probe with the Goddess-like mission.
So I think we over here at JPL, we always have a question that, well, we have some ideas of doing measurement for this type of model, that kind of model, but is this model itself interesting, right? Maybe there are many models, many measurement schemes can do many different things, but is it interesting beyond, say, 10 of us here? I think we probably need to, I don't know, I'm not a theorist, but I hope that probably some guidance from the theoretical part is more useful.
All right, thanks all panelists and people who were able to stick around. I apologize that we got off to a late start and a slow start, and that probably affected the number of people that could or did attend. Are there any other questions or final comments?
Yeah, this is Brad.
Yeah, go ahead.
And well, first I want to apologize too. I have no idea how we got this so screwed up, but I've spent, about the last hour doing nothing but scaling back and forth with people who are having problems, particularly like finding your session. And we'll have to run this over again sometime soon with the, a crisper connection information. But I would like to just suggest that with things like Goddess and experimental physics and space in general, it's a real challenge to build a broad base of support without an opportunity for multiple investigators to take part. You can't really work with just a single, compact science team and succeed in having a lot of people interested in the mission if they don't see how it could be something that the community can take part in. And so for something like Goddess, you really do need to make sure that you've got multiple different opportunities. That the questions that you're probing are broad enough and the capabilities are flexible enough that you can do at least a couple of different pursue a couple of different objectives with the instruments. Either that or you have to have an experiment that you can sign 50 or 100 people up to.
I think this is I think that's a very good point. And we've had a pretty small team largely at JPL working on Goddess to flesh out a concept. But as we think about turning a concept into an actual mission, that's really one of the things that we wanted or want to do is reach a broader base. And I think the talks we had today, in my opinion, were really good at sort of laying that out, and we've got some good people that gave the talks, obviously that I hope we can get involved, and we can use those talks, which I think are going to be posted online, to point other people to start that conversation going forward. So I think this has been a useful exercise in that regard.
Good, yeah. I'm glad you feel like we're making progress on that, and I hope in the future I'd like to see us figure out how to get a workshop focused on those general objectives, just to help the white paper response.
I think we're thinking about that, and Chris has either volunteered or Ben volunteered to take lead on thinking about a workshop next year. And so I think moving forward, one of the things that we'll do is think about what the right timing and format of a workshop would be. And I think that these 4 talks we've had today, in my opinion, form a really good basis for a potential workshop in addition to the white papers.
Right. And I would like to thank Ben Goodman too, who's undoubtedly been dealing with just about as much stress as me, trying to figure out how to get the right WebEx connection out to everybody. So thanks, Ben.
Yeah. Thank you both. And I think, you're both free to go have a celebratory drink now.
All right. I'll see you guys later.
Well, any other last minute comments or suggestions? And of course, thanks to Claire, who's already to tomorrow. Stayed on past midnight. So, okay, if there's no other comments or anything, then I think we'll break there, and we will definitely be in touch via email about how to proceed. And thanks everyone for helping set it up and for coming and a good conversation. It's some really good talks. These are actually very good reference material for me as well as I think about how to go ahead. All right, thanks all.
Thank you.
Have a good
Bye.
evening. Bye.